In the last video, we took a guess at what the solution was for our differential equation, and we came up with an exponential as our guess. And as we did the analysis, we developed a characteristic equation. We ended up with a complex answer for one of the adjustable parameters, the natural frequency of our circuit. So here's the form of our proposed solution. Now this is getting kind of complicated, but I promise you we're gonna simplify this pretty soon. We have two solutions for S1 and S2 that we plugged in as plus and minus j omega naught. And we have more adjustable amplitude parameters that we have to figure out. So now in this video, we're going to continue on solving our differential equation. This is our proposed solution. This is a pretty complicated looking expression. And what we're going to call on here now is something really important in electronics and in general, and it's called Euler's identity. And we're going to use this identity to figure out what to do with these complex exponential terms. So if you search on this term on Khan Academy, you'll find an explanation of where these identities come from. But I'm just going to state them right here. And what it says is that Euler's identity is e to the jx, anything up there, equals cosine x plus j times sine x. That's one of the identities. And the other identity is e to the minus jx equals cosine of x minus j sine x. So these are useful because we have this exponential function with the complex unit inside of it. When we go over to this side, this is a sort of a normal complex number. Cosine x is some number between plus and minus 1. Sine x is some number between plus and minus 1. And it's just a normal complex number. So this may help us simplify our life here as we move forward. All right, so that's a really important identity that we get to use to solve our LC circuit. Now I'm going to go back and rewrite these two exponentials using Euler's identity here. And this is going to get big, but it'll collapse down pretty soon. Okay, let me move over here. I equals K1 times e to the plus j omega t. Let's use this one here. So that would be cosine x is omega naught t plus j sine x is omega naught t, and we use the first one. Okay, now the second term is plus K2 times, now we have the negative up in the exponent, so we use this one, cosine omega naught t minus j sine omega naught t. Now we have our solution spread all out across the screen, and let's see if we can tidy things up here. So what I'm going to do is I'm going to gather all the cosine terms together, this one, and then I'll gather the sine terms together. Okay, so I equals cosine omega naught t, and cosine is multiplied by K1 and plus K2. All right. Now let's add to that. We have j sine and j sine, so I'll write sine omega naught t over here, and j times what? J times K1, and this time we have this minus sign that makes it minus K2. All right, So now, current is some number times cosine plus j times some number times sine. Now, these are two arbitrary constants, and I'm going to just make up another one. I'm just going to call this one A1. And we'll call this one A2. And we'll call that, I'll use the J, K1 minus K2. And this, now I can rewrite this as I equals A1 cos omega naught t plus A2 sine omega naught t. Good. So from now on, we're going to work with these a's, and if I ever want to know what the original k's were, I would just come back to these equations here. Once I figure out a, I can figure out both the k's. So let's keep pressing on. How do we figure out A1 and A2? To do that, we're going to use the initial conditions, the ICs. And if we think back, we remember that in our original schematic, we had some Q here, which means we had a plus or minus V0, V naught. And we said the current through here started at 0. So that's our initial conditions. V of time equals 0 equals V naught, and current of time equals 0 equals 0. Let's use these two values to help us figure out what A1 and A2 are. And we'll do that in the next video as we continue the derivation of the natural response.